Welcome to Pomegranate Health, a podcast about the culture of medicine. I'm Mick Cavazzini for the Royal Australasian College of Physicians. In June 2024, US astronauts Sunita Williams and Butch Wilmore blasted off from Cape Canaveral to the International Space Station for a mission that was supposed to last 8 days. But on docking with the ISS, their brand new Boeing Starliner lost function of 5 of its 28 thrusters. Rather than scramble a rescue vessel, NASA and the astronauts agreed that they would keep working on the station for the next scheduled transport. But that wouldn't be until 9 months later, with the arrival of a Dragon capsule from Elon Musk's company SpaceX. Williams and Wilmore barely had a change of clothes with them, and by the time they splashed down off the coast of Florida last March, they'd clocked up 286 days of flight time. The footage of them being stretchered from their re-entry vehicle prompted feverish speculation in the media about their changed appearance. The most morbid of the many headlines I saw came from the UK's Daily Mail, which screamed, "Rescued NASA astronauts stun the world with their frail and gaunt appearance. How their bodies have been ravaged by the void." Reporters were fascinated by the wispy white hair poking out from Williams' helmet, not imagining that perhaps the 58-year-old had simply not thought to pack hair dye for the brief sojourn to the space station. She really didn't look any more dehydrated and exhausted than I do after a long-haul flight. But it seems that even veteran NASA astronauts get judged on their looks. And space travel does have several fascinating effects on the human body that aren't immediately visible, or all that well understood. NASA's Human Research Program bins the risks into 5 categories. At the top of the list is concern over the exposure of astronauts to cosmic radiation, which can be reduced to some degree by shielding of space habitats. However, the impacts of microgravity on sensory motor pathways and bone density are much harder to engineer away. In the second episode of this 2-part series, we'll get into how the cardiovascular system adapts in space, and discuss the management of a case of suspected thrombosis from a few years ago. Medical care on orbit has many surprising parallels with the remote medicine you're already familiar with. But what happens when we build a base on the Moon? Around mid-2027, NASA's Artemis 3 mission is expected to land people on the Moon for the first time in 53 years, with a spacecraft called Orion. Components for a lunar base would be delivered a year later, with the expectation that rotating crew would be inhabiting the outpost continuously by the early 2030s. And the ever-humble Elon Musk reckons he'll be sending people to Mars by then too. Voyagers will be signing up for a 9-month trip in each direction, and probably a 2-year mission in total. To guide me through all this, I invited 3 specialists who provide advice on systems and apparel that would keep astronauts safer as they broach new frontiers of exploration.
My name is Professor Gordon Cable. I'm an honorary professor also at the Australian National University. My training has been in aerospace medicine, working predominantly for the Air Force for the majority of my career, and had the wonderful opportunity to be seconded to the Australian Space Agency for a couple of years. Currently working with my own company, Human Aerospace, on space life sciences projects.
Thank you. Alicia, tell us your background.
So Alicia Tucker, I work as an emergency physician. I practice down at the Royal Hobart Hospital. Born and raised in Tassie, so I've subsequently branched out into being a fellow with the Academy of Wilderness Medicine, as well as I actively work as a diving and hyperbaric physician. I'm an aviation medical examiner with CASA, and I'm in a coordinator role with the University of Tasmania as a senior lecturer in the health care in extreme environments qualifications.
Fabulous. John, you're a recent arrival in Hobart, I believe.
Yeah, that's right. Only a couple of weeks ago, actually. Yeah. So my name's Dr. John Cherry. I'm the Deputy Chief Medical Officer at the Australian Antarctic Division, a rural generalist, GP anaesthetist and emergency physician. I'm also the Vice President of the Australasian Society of Aerospace Medicine, and sit as the space analogue representative for the international collaboration of various national Antarctic programs from around the world, and have had the opportunity, fortunately, to work for both NASA and the European Space Agency as well.
Cool. And my co-pilot on this mission is Associate Professor Chris Leung. He's not just a valued member of the podcast editorial group, but Chris, you stop me from nerding out too much and ask some of the clinically relevant questions.
Yes, I'm a gastroenterologist, and I'm also a consultant in general medicine at Austin Health. And outside of this, I'm Deputy Chair of the Board of Doctors for the Environment Australia.
As already mentioned, cosmic radiation is the more apparent and most quantified medical risk of prolonged space travel. In my reading for today's podcast, I leaned heavily on one review for NPJ Microgravity titled Red Risks for a Journey to the Red Planet, and another for the journal Life titled Space Radiation, the number one risk to astronaut health beyond low Earth orbit. Solar events are not the most likely source of radiation for astronauts, but they're certainly the most dramatic, and their frequency ebbs and flows over an 11-year cycle. The most intense are described as having as much energy as 1 billion hydrogen bombs. As these bursts of electromagnetic radiation travel close to the speed of light, they take just 8 minutes to reach the Earth. Accompanying big flares, you also have massive ejections of coronal plasma, which generate so-called proton storms. These fronts can take minutes to hours to reach the Earth, but fortunately we're shielded from most of this radiation by the Earth's magnetosphere. The awesome aurora that are seen at high latitudes occur when proton particles skate along the magnetic field lines towards the poles, where they ionize molecules in the atmosphere. These ions can themselves wreak havoc with high-frequency radio transmissions. In fact, in May 1967, at the height of the Cold War, US Air Force Command thought that the Soviets were jamming their ballistic missile early warning system, and were ready to scramble nuclear bombers in retaliation. Proton storms can penetrate hardware and damage componentry, so spacecraft are typically constructed with aluminium shielding. Also, the International Space Station and the very new Tiangong station from China still get some protection from the magnetosphere, given that they operate only 400 kilometers above sea level, in the low Earth orbit mentioned before. However, the Moon is much more exposed to the elements, as would any astronaut be conducting an extravehicular activity clad in nothing but an EVA spacesuit. The most energetic solar event of the space age took place in August 1972, when a large sunspot underwent 10 days of eruptions. Just a few months on either side of this were the moon landings of the Apollo 16 and Apollo 17 missions. According to NASA's radiation health officer, anyone going for a moonwalk at the time would have experienced around 4 sieverts of radiation, and even crew taking shelter in the command modules would likely have received exposures of several hundred millisieverts. I asked Professor Cable to describe the effects of such acute doses, had there been astronauts on orbit at the time.
So 4 sieverts is an extremely large dose of radiation for humans, 4,000 millisieverts. I mean, if they had been on the surface during that time without protection, only the protection of their suits, a 4 sievert dose with an acute exposure would result in acute radiation sickness and death within, a matter of days or weeks. On the spacecraft itself, they may well have got some mild symptoms, but, in those sort of doses, it really comes down to cumulative dose. Of course, all these effects are probabilistic, so you can't say that a particular dose will definitely result in a particular disease, but it would certainly result in increased monitoring over the lifetime of an astronaut.
You're stealing my thunder. I'm going to get into the cumulative dose stuff. There was another solar event in 1989 where control was lost over some satellites for several hours, and there was a 9-hour power outage in Quebec. And there were humans in orbit at the time. The Space Shuttle Columbia experienced malfunction in a pressure sensor in one of its hydrogen tanks. And cosmonauts on the Mir space station reported seeing flashes of light, even with their eyes closed. In an analysis of radiation measures from that space station, it's been estimated that had the crew been on an interplanetary mission far from the protection of Earth, they might have copped a dose exceeding 1,000 millisieverts. These days, the shielding is a lot better, probably twice as thick. Future moon bases would have storm shelters with even more protection. And am I right in understanding that solar ejections, you can predict them by observing sunspots, and, the further you are from the sun, the less chance there is of getting hit? There really isn't that much chance of astronauts being unprepared for a major event. And so
I can speak to this with some level of accuracy, because in a prior life I was an astrophysicist, so I'm quite familiar with the sun's activity, and there is continuous monitoring of the sun's surface through a range of different satellites, looking at a range of different wavelengths of energy, and it depends where you are. It depends how quick the ejection is, and the volatility of that ejection as to how much warning you'll get, but there would be some warning to allow the astronauts to shelter in place and try and prevent the maximum damage. Yep. But the actual practicality of that is we've got astronauts in a capsule, in a craft, on the surface of another planetary body. One of the challenges with shielding in a spaceflight environment relates to mass and volume. So if we're here on Earth, you can put up a whole bunch of lead shielding, and that's going to provide you with some excellent protection because lead is so dense, so it prevents some of that radiation coming through, not all. But obviously you can't transport a whole bunch of lead to space without expending huge amounts of energy and huge amounts of money to do so. So the current thoughts around polyethylene or utilising water as a shielding medium as well. So actually having shielding, like the water for the mission in a particular area of the capsule, and they can shield in there, which has been utilised previously. There's thoughts of personal kind of protective equipment that the astronauts can wear as like a final measure of shielding. And if they're on a planetary surface, utilising, for example, lunar regolith, which is the material from the moon's surface, and creating that as a shield over the top of a structure. But these are issues that are ongoing, and it's about balancing the risks of that the best we can, but we can't mitigate all of those risks.
I have a colleague at ESA, Anna Falkman, who's the radiation specialist. When the first Artemis mission flew, there was a lot of radiation monitoring equipment, and I think that they came up with quite a lot of surprises. And I'm not in a position to share some of that information, but I think that they hoped that, say, the back area of the capsule was going to be able to be where you could retreat to, but in fact, the radiation exposure was surprisingly higher. So I think it's really in a state of flux, to use a bit of a radiation term.
Now, these solar events are the ones that make the science fiction movies, the space movies, most dramatic, but NASA tends to be more or equally concerned with galactic cosmic rays. Now, GCRs are generated by exploding stars in a galaxy far, far away, which fire off not only energized hydrogen and helium ions like we've described, but also some heavier particles known as HZE ions. So the HZ stands for high atomic number, as it includes particles all the way up to iron, cobalt, and even nickel at Z28. And the E in HZE stands for energy. So despite making up only a tiny component of the galactic radiation, the high energy of these particles makes them more dangerous. Gordon, can you explain further?
Sure. As you said, they're less frequent in number and in terms of the flux of particles, it's less dense than what is coming from the sun that we were just talking about, but it is much higher energy. And as you said, some of these atomic nuclei are very high atomic numbers, are highly ionized, traveling close to the speed of light. And you can imagine that bowling ball going through the macromolecules of your cells and the disruption that would cause the oxygen-free radicals that are created, the ionization that occurs in the tissues is damaging to genetic material. It's certainly, potentially down track going to lead to malignancies. It leads to secondary radiation being released to whatever it hits, basically spacecraft structures or the body. Secondary particles, subatomic particles will be released, and they can also be ionizing. So they are more damaging, and they're ubiquitous. They're coming from every direction because, as you rightly say, they're generated by exploding gas clouds and supernovas and star systems throughout the galaxy, so coming at us from every direction. It's hard to shelter from that if you're out in deep space. The consolation is if you're on a planetary surface such as Mars, you're at least shielded to some extent by the bulk of the planet that is behind you, but you're still getting the flux of radiation coming at you from the top. We, out on the Earth, are kind of sheltered in this protective bunker, but that's an unusual situation. Out there, the cosmos is this seething, boiling soup of really highly ionizing radiation.
Chris, you want to pick up the next question?
Yeah, absolutely. So on Earth, we absorb about 0.3 millisieverts in a year from these galactic cosmic rays, which is about the same as about what we get from radioactive isotopes in our food. So from a gastroenterologist perspective, Brazil nuts are naturally radioactive because they've got these deep roots which absorb high levels of radioactive isotopes. But by far the majority of natural radiation comes from the radon gas we breathe, bringing the total to about 3 millisieverts in a year. So as we talked about before, about a crew operating at lower Earth orbit, they would expect to absorb at least about 70 millisieverts from galactic cosmic radiation over a year-long mission. How does this sit within the limits established by workplace safety regulators and NASA themselves?
I looked up a little bit of data there to inform that. So 20 millisieverts a year is your typical radiation worker dose limit. The information I've got here is that on the ISS, you would get probably in a 12-month mission somewhere around 300 millisieverts. NASA's current career dose limit for low Earth orbit is 1,000 millisieverts. And, it would be very easy with recurrent doses like that for astronauts to exceed radiation dose limits. But that career dose is very much based on risk acceptance in the sense that they will accept a 3% excess lifetime risk of cancer in the astronaut population. So it's dependent upon gender, with females having a lower dosage range than males, but also age, in the sense that the older you get, the bigger the limit becomes, because the older you are, the less time you have for cancer to develop before you would die of natural causes anyway. For example, a male at age 25 would have a career limit of 1,500 millisieverts, whereas a male astronaut at age 55 would have a 4,000 millisievert dose. They would be the more likely candidates to probably go on a mission to Mars with all that expertise. So it is really age-dependent, gender-dependent, but also a risk acceptance of a certain threshold of cancer risk.
I can take a swing at that if you like. I think, this is a new paradigm for space travel. The idea of the Apollo missions was to go to the moon briefly and then return to the Earth. The new paradigm is to put astronauts on the moon for extended periods of time and then utilise that as a stepping stone to go to Mars, which is, again, a completely different paradigm away from that magnetic shielding that Earth provides us with. One of the challenges that NASA is trying to grapple with is how do we put people into these environments in a way that isn't going to debilitate them either acutely or in a chronic way. Looking at the numbers involved, a return trip to Mars would currently give an astronaut their lifetime exposure of radiation. So there's not only the medical components that we need to think about in terms of short and long-term risks to their health, but there's also the selection and training components, because what we're effectively saying, if NASA maintains the same requirements, which we expect that they will, is that the opportunity for these astronauts to train on the space station as you would expect at the moment for a 6-month mission before you then deploy for a longer mission onto Mars, those opportunities won't be available because they'll exceed their lifetime limit of radiation exposure.
Galactic cosmic rays aren't just a risk, potential risk in terms of increased cancer incidence, but they also do damage proteins, cause oxidative stress. There's a bunch of literature on the range of non-cancer forms of tissue degeneration, which includes cataract formation, premature aging, effects on atherosclerosis and angiogenesis. Do we know enough about these to put any numbers on them, or is the epidemiology just really lacking?
Epidemiology is lacking. The total humans that have gone beyond low Earth orbit, N equals 12 to the moon, really. Now we're going to get another 4 next year, hopefully with Artemis 2, but a lot of those things are theorised, again, based on Earth-based studies. A lot of the data and knowledge that we have about radiation exposure, those other tissues, come from radiation exposures on Earth, nuclear weapons, nuclear accidents, all that kind of stuff. And there is some evidence, for example, that angiogenesis, cardiovascular disease, endothelial damage might occur as a result of radiation exposure in Earth-based populations. But it's hard to extrapolate that to the space-based population because we don't have the N, and of course we don't have the number of females at all. We have no data on female astronauts in deep space at all compared to the N of 12, which were all male. So lots of unknowns there.
Of the 730-odd people who have visited space, just under half did so with the shuttle program, on missions typically lasting a week or two. Most of our understanding about long-duration exposure comes from the International Space Station that has been crewed since the year 2000, and the Soviet-Russian Mir station, which was decommissioned a year later. Between them, they've had 394 visitors, with an average expedition duration of 6 months. Even so, there still aren't enough data points to weed out all the personalised factors that could confound incidence rates of cancer and other such diseases. Some of what we know about the effects of galactic cosmic radiation comes from animals or cell cultures housed on the space station. In terrestrial models, HZE ions may be generated by particle accelerators, but those aren't cheap experiments to run. We don't have time to go into all the findings and caveats associated with this more basic research, but I do just want to touch on the potential effects of radiation on the brain. Cancer radiotherapy has long been associated with fatigue and brain fog, and proposed explanations include demyelination of neurites, free radical damage, and breakdown of the blood-brain barrier. In rodents exposed to simulated GCRs on Earth, researchers have observed impaired performance in learning tasks and reduced dendritic spine density in neurons of the prefrontal cortex. This was discussed in a very recent review for The Conversation, where it was suggested that antioxidants could have a protective effect. I should note there's not much evidence of major cognitive deficits associated with spaceflight to date that couldn't otherwise be explained by the stress of confinement and disrupted sleep patterns. Just look at the simulation the Russian Space Agency conducted in 2012, where 6 participants were confined to a mock habitat in a Moscow car park for 17 months. Only 2 of the 6 men adapted without any negative behavioural symptoms, while the 2 at the other extreme respectively showed impaired performance on a psychomotor vigilance test and positive scores on a depression screening tool. Whatever the cause, it's important to understand any deficits that astronauts might experience which would affect their ability to cope with operational tasks and emergencies. There are neurological symptoms experienced by some, such as impairment of smell and vision, that may result from the effects of microgravity. While doing weightless tumble turns looks like fun, one of the most immediate consequences is the shift of around 2 litres of blood and other fluids away from the legs. This hydrostatic shift also impacts the retina and function of the circulatory system. Here's Gordon Cable again.
Microgravity has the initial impact of removing that hydrostatic pressure gradient in the body as soon as you go to space, just simply because the gravitational force that normally pushes all the blood down towards the feet, there is an immediate redistribution of fluid from the lower body to the upper body. So astronauts, from a physical perspective, notice swelling in the upper body, so the face becomes puffy, nasal passages may become congested, the distension of the neck veins, and conversely, in the lower limb, the legs get thinner as the fluid redistributes. And that then leads on to a number of secondary effects. For example, the increased perfusion through the kidneys with the centralisation of fluid leads to a diuresis, so a loss of plasma volume, a hemoconcentration initially, so a decreased volume but increased red cell mass. There is a deconditioning or a slowing, if you like, of the heart's responses, in the sense that the myocardium will start to atrophy somewhat because it doesn't have to work as hard against gravity gradients, and baroreceptors probably lose a bit of their sensitivity in responding to blood pressure change as well. So all these secondary effects come after that initial fluid shift. The effect on blood pressure is probably not huge. There's sort of minor fluctuations, but it doesn't have a hugely detrimental effect on blood pressure either way. But there's some very interesting data that's coming out, or theories coming out, about not just the fluid shifts themselves, but the effect of the hydrostatic gradients within the tissues and how hydrostatic gradients compress vessels within the body and change flow. And astronauts, as a result of that, with these deconditioned cardiovascular reflexes, when they come back to Earth, of course, the risk then, the problem that they face is orthostatic hypotension, because they can't mount the same cardiovascular response to gravity that they once could. The body is an amazing machine in the way that it adapts to an extreme environment, but then if you come back to Earth, you've got to readapt back to that original environment, which again has a process behind it and takes some time.
It's fascinating, the physiology, isn't it? But one of the other top risks is spaceflight-associated neuro-ocular syndrome, or SANS, which is thought to result from increased blood pressure in the head and neck, or that exactly what you're just talking about, Gordon. And our understanding, so typically presents after a month in orbit, but sometimes sooner. And one of the common signs is this enlarging of the blind spot. Could you explain more about, spaceflight-associated neuro-ocular syndrome, what's going on, and what are some of the implications?
Yeah, I'll take that. I think this is a really fascinating subject because it is a really good example of where operational aspects of spaceflight butt against healthcare aspects of spaceflight, and the two interact. So this was first noticed when a couple of astronauts were in flight and realised they couldn't quite see as clearly as they had done on the ground, and needed to utilise some glasses to do so. And it was really because they acknowledged that challenge and they acknowledged that difficulty with their support team on the ground, that's why we even know about this particular medical condition. you're absolutely right. It's theorised that this is due to fluid shifts to the head as a result of being in a microgravity environment. And until very recently, there was really no way to predict who was going to be affected. So it was a lucky dip almost as to who would become affected by this. There is some evidence now that there's maybe a genetic marker that may be linked to this, but there's still some more research that needs to be done on that. It's certainly not definitive. But the challenge of this is effectively what you're getting is folding of the retina on the back of the eye, which affects the visual acuity of the person. So if you compare a retinal scan of a normal eye and someone who has spaceflight associated neuro-ocular syndrome, what you'll see is in someone who has SANS that the actual the retina at the back is sort of folded over, and you get this kind of wave effect, and you can see that on a retinal scan. Very difficult to detect in space without that technology unless you're just assuming it from a visual acuity perspective. But the reason that I mention the operational component with all of this is because quite clearly if you're putting astronauts into space for an extended period of time and then you're asking them to land a craft, if you can't see properly, well, that creates some pretty significant issues for safely piloting that vehicle and landing it on the surface. Equally, if you're exploring the planetary surface, if you can't see properly, doing an EVA on the surface of the planet it risks higher rates of trauma and therefore medical complications and mission implications for that as well. It actually has real operational implications, which is why so much energy has been put into it over the last few years.
And it could be long-standing, I understand, is it?
Absolutely. So some people recover quickly, some people recover slowly, some people never recover. Again, that has long-term implications, not only for the flight, but, we're putting patients, the astronauts are patients, we're putting them into an environment where we're risking their health and providing challenges to their health, and we have an obligation to support them when they return from that environment. And, if that's affecting someone's vision for the rest of their life, that has implications for future, careers and life when you return back to Earth as well.
Yeah, we recently got a retinal camera in our emergency department, which is fantastic, but also our MD research students are using optical coherence tomography in their research. Is that something that can be used, or other tools that can be used to perhaps get more data in this space? Or has that already been done?
Yeah, it's already been done. They certainly use them. Ultrasound is the only radiological imaging technique on the ISS, but they can certainly do retinal photography, fundoscopy. I think they have an OCT up there as a result of this problem. They can do scans. So that scanning can be done on orbit, but anything more complex than that, when they come back, they can have MRIs done, but that's not possible in space. But yes, there's certainly imaging done as part of the research program behind this.
I think John has already described what you would call chorioretinal folds, which occur in about 20% of the handful of astronauts that are tested. Then there is also this posterior flattening of the ocular globe that basically gives you long-sightedness. That is something that you can correct in flight, I understand.
Yeah, with glasses, essentially. You can use lenses in order to change the optics because of globe deformation, but you can't really do much about the issue of that kind of retinal thickening or edema. There's nothing that we can particularly do that's corrective. I mean, all of these things are they being compounded by other environmental issues, such as the fact that you've got no convection of air, and therefore the individuals have got a relatively higher level of carbon dioxide proximal to them. Carbon dioxide does cause vasodilatory and other effects depending on which part of the body. Is it that we need to be thinking about other interventions, not just corrective issues, but actually other interventions which are completely not related to the fluid shifts or the genetics? Is it about salt intake? Is it about that carbon dioxide concentration being up too high? Because it's about tenfold higher level of carbon dioxide on the station. So it is one of the priorities for a good reason. It's a fascinating field. That
tissue pressure gradient thing I mentioned earlier certainly plays into this argument, Mick. But I was going to say, in terms of risk mitigation here, glasses, spectacles, that's the ambulance at the bottom of the cliff. We need to build a fence at the top. And the research directions are looking at mitigations of the microgravity fluid shift problem. So things like revisiting the lower body negative pressure technology to try and draw fluid away from the upper body back down into the lower limbs. That's been used for a long, long time, but they've been obviously looking at that in regards to SANS and protection. Human Aerospace has been working on thigh cuffs, which are essentially tourniquets to try and keep fluid trapped in the lower limbs in microgravity, trying to come up with wearable, adjustable, tolerable devices that can do that. But in fact, the papers, the authors that wrote this research on the tissue hydrostatic pressure gradients suggested that even lower body positive pressure might work better than lower body negative pressure in mitigating SANS for various reasons. So there are a number of research areas and directions that are being explored to try and get to the bottom of preventing it happening in the first place, rather than having to find some space optometrist, which I think will be a new subspecialty of optometry in the future.
Yeah, I think we've covered some of this already, but the eyes being not only windows to the soul, but windows to the brain, and there is almost 11 to 15% ventricular enlargement, given that we're now doing pre and post free Tesla MRIs of brain and orbits in all NASA crew members since 2009. And this increase in ventricular enlargement in the brain has been detected in astronauts and cosmonauts by multiple investigators now. Is that still to do with fluid pooling or some other mechanisms?
Yeah, look, that's a good question. I mean, I think the spinal column, is a column of fluid like every other column in the body, organised in a Z direction, a GZ direction. So it's logical to expect that cerebrospinal fluid would redistribute in a similar way, but you would think that the pressure gradients would remain relatively constant across those cisterns and those blood vessels. So I'm not sure what the explanation of the dilated ventricles are. I mean, it's very hard to measure intracranial pressure on orbit. Let's face it, it's a gravity-dependent process, and there's no real direct measure. There's been a group in Western Australia, I think at UWA and the Lions Eye Institute, that have been looking at venous plethysmography of the retina as a sort of an analogue or a proxy measure of intracranial pressure. But I don't think there have been any good studies to actually demonstrate that intracranial pressure rises markedly, and probably less so in orbit than it does even in head-down bed rest tilt studies on Earth. What would explain that ventricular dilatation? I must admit, I'm not entirely sure. One of the other things we see around the ventricles of the brains of astronauts in some cases on MRI after return are white matter hyperintensities in increasing numbers compared to what you would expect just through aging. And we see similar white matter hyperintensities in other areas of the brain, not around the ventricles, in military crews who are exposed to hypobaric environments, low pressure environments, either in chambers or at altitude. It's also been hypothesized that while still high functioning, the white matter hyperintensities may lead to a slight decrease in baseline cognitive function compared to their previous measurements. Now, whether that's a manifestation of the microgravity interacting with hypobaria, interacting with potentially pressure changes within the brain or fluid shifts, isolation and confinement, it's very hard to model that on Earth because we can't get that same radiation, we can't get that same microgravity for the length of time. And all those stressors on the body probably do have some kind of synergistic interaction at this stage as yet unknown.
There's so many fascinating effects of space travel on the body that we don't have time to go into. But you'll find heaps of useful academic literature embedded in a transcript of this story at racp.edu.au/podcast. Observation of astronauts has shown that they experience delays in wound healing and reactivation of latent infections such as herpes virus and cytomegalovirus, suggesting that immune function too is affected. In a 2023 paper in the journal Frontiers in Immunology, it was shown that expression of more than 15,000 genes from the leukocyte transcriptome were disrupted over months-long missions to the International Space Station. Expression levels returned to normal after some weeks or months back on Earth. NASA's Gene Lab has thrown all the other omic technologies at ISS astronauts as well. The strongest signal from their 2020 publication was for mitochondrial stress, but also changes to inflammatory and cell cycle markers. And then there are the occupational hazards of actually exploring the foreign Martian landscape once humans actually get there. You know from the movies that Mars is famous for its dust storms, which could well cause interference to solar panels and wear on mechanical components and EVA suits. But Martian regolith contains some pretty toxic mineral components too. There are perchlorate compounds on Mars which have thyroid impacts, trace amounts of arsenic which is neurotoxic and carcinogenic, and also hexavalent chromium, the industrial pollutant made famous by Erin Brockovich. Even the basic quartz silicates that make up much of our moon's dust can be an irritant. Some of the Apollo astronauts reported hay fever-like symptoms and a smell that resembled gunpowder. At 20 microns or less, it will not be a trivial affair to prevent any contamination of a habitat's air systems. Other risks of extravehicular activity that you probably hadn't thought of are decompression sickness and hypobaric hypoxia. The bends is classically associated with scuba diving, of course, where respiration of air at pressure dissolves nitrogen into the bloodstream. It's when divers return to normal pressure and the nitrogen reverts to a gaseous state that bubbles form in the circulation with painful and potentially lethal effects. When you move from a spacecraft to an EVA suit, there's a drop in air pressure that's equivalent to being whisked to the summit of Mount Everest. Those cumbersome Marshmallow Man suits you see on a spacewalk are only pressurised to 4.3 psi, or less than a third of pressure at sea level, which is what the International Space Station is kept at. In order to reduce the probability of the bends, astronauts wash out nitrogen from their tissues by doing a pre-breathe of pure oxygen for 4 hours before a spacewalk. This technique has been known since the Second World War, but comes with the problem that it consumes time and valuable O2 stores. In more recent years, NASA has modelled and experimented with different pre-breathe protocols, such as stepping down in pressure the night before and speeding up nitrogen washout with light activity. I'll leave you with some audio from June 2024 of NASA's Mission Control advising ISS crew on how to provide first aid for an astronaut suffering decompression sickness.
Thank you for clarification. So if we could get a commander back in his suit, get it sealed, and step into procedure 5.180 for suited hyperbaric treatment.
It was a bit of an embarrassing scene for NASA because this audio came from a drill that was accidentally broadcast to the public. They quickly clarified on social media that, quote, "There is no emergency situation going on aboard the International Space Station." But we will hear a real case study from the ISS in the next episode, as well as the strange effects of microgravity on bone mineralization and on cardiovascular fitness. I'm Mick Kabat-Zini. Catch you then.
Is the big problem, and given his exam, I am concerned that there are some severe DCS hits, and so I would recommend trying to get him in the suit as soon as possible. Copy. Understand that this is a best effort treatment, and so whatever you can do is going to be better than doing nothing. So is there a way that we could get the suit over the head, have the visor open, and put the mask at least close to his face while you finish sealing up the suit, or is that not feasible? Perfect. So yes, then I would like you to have 100% O2 flowing via mask while you get the suit on. Prior to closing the visor and pressurizing, I'd like you to do a pulse check one more time and then step into 5.180, section 3.